Log on, tune in, find out. Another good idea from Cambridge.
Those of you who are already in Cambridge, welcome to the Maths Department. This is the London Mathematical Society Invited Lecture Series. This is an annual lecture series sponsored by the London Mathematical Society. And I don't know when it was last in Cambridge, but it's at least 12 years since it's been here, so we're very grateful to have it here now. The idea of the week is that there'll be, I think, about 12 talks in total, 8 of them given by Emmanuel Candace, who I'll introduce properly in a moment, and then 4 others. So our main speaker is Emmanuel Candace, and he's French, did his undergraduate at the École Normale. But he's been in California for about 15 years, first at Stanford, where he did a PhD with David Donahoe. He stayed at Stanford as an assistant professor, but then moved to Caltech, where he spent about 10 years. And now he's back at Stanford as a professor there. And he's won quite a remarkable number of awards. Certainly the most prestigious, I would say, is the Alan Waterman Award, given by the NSF. And that goes to a mathematician about once every 10 years, as far as I can tell, and it's worth about $500,000. So that's quite a serious prize. But he's also won the Polyer Prize. He was a Sloan Fellow. And I could go on, but I won't. So without further ado, let me introduce Professor Emmanuel Candace, who's giving these lectures on compressed sensing.
Okay, thank you very much for the very kind introduction. I have to turn the microphone on. I have to correct one thing right away, and that's, unfortunately, I did not go to the École Normale. I went to the École Polytechnique, and there's a bit of a rivalry between the two, just like two prestigious universities in England. And I see some people from the École Normale, so I just thought I should correct this. Okay. So I thought I would start by actually giving you an idea of the plan of the lectures. This is subject to change. Of course, coming here, I did not know exactly what kind of audience to expect, whether this would be the mathematical type or the engineering type or a combination thereof. And so this lecture plan is subject to change depending on perhaps feedback I could get. But basically, we have 8 lectures, and the goal of these lectures, the agenda for each of these lectures is something like this. Today, we're going to talk about, it's going to be a glossy introduction to compressed sensing, and then it's important for me to show you some history. That is, where do these ideas come from? We're not the first one to do what we do, to give you a sense of historical perspective of the subject. Then lecture 2 will describe a probabilistic approach to compressed sensing, which is a novel theory of compressed sensing, which is a year old. To discuss another approach to compressed sensing, which I would like to call it a deterministic approach. And then if people are mathematically inclined, there are some delicate results in the theory. And I thought I could spend a lecture explaining what kind of probabilistic tools we need to actually prove these sampling theorems. Then in the second part of these lectures, we're going to start to kind of ease off and talk more and more about the real world. I thought that the 5th lecture could be dedicated to a noisy issue. So what happens when we have undersampled data that are on top of this contaminated with noise. 6, I would like to talk about a new topic, which is matrix completion, which comes on the heels of compressed sensing, but it's a topic in itself, showing you how some of the ideas developed in the context of compressed sensing have much broader applicability than compressed sensing itself. And then finally, the last 2 lectures, 7 and 8, of course, the first 6 lectures are fairly conceptual, discussing the theory of recovery of interesting objects from undersampled data. But in practice, to recover these things, we need to solve large-scale optimization problem, and I want to kind of address this. How do we do this? And 8, one of the exciting things about compressed sensing is that it has lots of applications. In fact, people are designing novel acquisition devices to implement these ideas into effective hardware. and I would like to review some of this progress. Okay, so the agenda is fairly conceptual at the beginning, and towards the end of the week, a bit more applied. Okay, I think what I'm interested in knowing from you is whether you're up to some math to kind of show, how these kind of theorems actually are proven. Okay, so for the first lecture, as I said, I would like to show you some history and offer a glossy introduction to the subject. We're going to talk, all these lectures are concerned with underdetermined systems of equations. We're going to learn through these lectures that convex optimization often returns the correct answer, even though we think we cannot solve this underdetermined system. If we make some assumptions about the right-hand side, then we'll see that we can invoke convex optimization to get what we want, which is a bit surprising. I would just want to show you some early examples of sparse signal recovery, show you some early results, and at the end, kind of give you a general introduction to compressed sensing. Okay, so let's get started. So we're going to start discussing underdetermined systems of linear equations, and of course these occur everywhere in applied science and engineering, and so I'm going to introduce some examples. Okay, so just to get things started, to set up some notations, we have b equals ax. X is a vector in Rn. X will always be in Rn, as far as I'm concerned. And the number of rows of the matrix A is m. So we remember this as m being the number of measurements, m for measurements, and n to be the standard dimension of a vector in Rn. So now we have a fat matrix like this. We observe Ax, and the goal is to recover X. And the problem that we have is that we have far fewer linear equations than unknowns. Okay, so this comes up all over the place, and I'm going to discuss a few examples. The first example comes from genetics, where people are interested in finding locations on the genome that could influence a quantitative trait. For example, as an example, we might be interested in cholesterol level. So the idea is to relate cholesterol level to your genetic makeup, and a model that people use in genetics is as follows, where I'm going to try to link this quantitative trait, which is here y. For example, the measured yi would be the coordinate of y would be the measured cholesterol level in patient number I. And A would be a matrix which encodes some kind of genotype information. Okay, so some kind of genetic information. So one matrix that people might want to use is a matrix Aij, where I relates to patient number I, and J relate to a location on the genome. And for example, what Aij might be is the number of alleles of a certain type at that location. Okay, and then we'd like to correlate, if you will, or to relate cholesterol level with genetic makeup. And so what people write down is a linear system that looks like this, where cholesterol level is A times X plus some noise, where Z is, of course, those are environmental factors that cannot be accounted by genetics. And in this type of applications, we would like to solve another determined system to actually find out which locations on the genome have an influence on high cholesterol level. And the kind of data sets that people deal with are, well, how many places on the genome do you like to test? Well, about 500,000 in a million. The problem is, how many people do you have in your study? Not many, maybe a few thousands, and so we have a very highly underdetermined system of equations to solve. Okay, that's our first example. Our second example is for example, in spectroscopy or in microscopy. We could have a camera or microscope or whatever this is. Let's say we have a microscope, and we all know that when I want to image a sample, I have a transfer function, which is a response of the microscope, and typically a transfer function would something look like this. So this is a Fourier transform of the impulse response of the microscope. And what the microscope does, as we all know, it's cutting out frequency, so you cannot get infinite resolutions. Okay, so what we get to see is an incoming image convolved with this transfer function. And so what we can think about this is as cutting out the high frequencies. Okay, so we would like to reconstruct a signal or an image with high frequency content, but actually the microscope is actually cutting out the high frequencies. So it's like saying that all of these equations, all the high frequency information is not available, and therefore we have another determined system of equation to solve. The problem that really motivated compressed sensing from the start is a problem in magnetic resonance imaging, which is a wonderful imaging modality to actually image living tissues inside the body. And the way it works is by magnetic resonance, which is by essentially subjecting a patient to a strong magnetic field and then lighting up RF fields, radio frequency fields. You can actually have hydrogen nuclei produce a rotating magnetic field that you can record, right? So it's a very complicated, the physics is quite complicated. If I want to discuss the physics of magnetic resonance imaging, I would have to start with the Bloch equations. So I'm not going to do this. I'm going to say that it's an apparatus that by essentially you can excite nuclei so that they will start rotating. Because they rotate, they create a magnetic field which you can measure. The thing is, in magnetic resonance imaging, we can make the excitation depending on space. And so the goal is going to be to recover the proton density inside the body. So you're going to excite protons differently at different locations. These protons will emit a magnetic field that you can record, and out of this recorded magnetic field, you would like to infer the proton density. Now, the mathematics of MR is quite simple. Once you make lots of approximations, what you actually measure at the end of the day are Fourier coefficients of a density of interest. So an MR scan is essentially measuring the Fourier coefficient. So we have a two-dimensional image here, ft1 and t2. And what an MR scan does, it essentially measures the Fourier coefficients of the density, the object f of interest. And of course, it returns the Fourier transform of the object of interest plus noise, and our MR data are extremely noisy. And in the noise, there are lots of things. There's the noise of the instrument, of course, and there's also all the approximations we've made along the way to say that the mathematics is as simple as observing the Fourier transform. Okay. So each time you collect a measurement in MR, you're actually measuring a Fourier coefficient, a single Fourier coefficient of the object of interest. Now, as I said before, MR is a wonderful, so we cannot see images better than this? Not really, okay. So we're going to have to do a lot of math then. Okay. So this is a typical scan of an MR scan. And the problem with MR, it's absolutely wonderful. There are things you can see in MR that you cannot see on CT scan. For example, CT is not good at showing you the difference between the living and dead tissue, but MR can. And so MR scans are really wonderful. The problem with MR is that it's extremely slow. That is, the acquisition time to actually make up a high resolution image is long. And that has lots of limitations. It means that it's almost impossible to come up with high resolution scans because, of course, people will move, so everything will be blurred. It means that the throughput through a scan is very limited, and these pieces of technology are very expensive, so that's not good either. If you cannot make a high-resolution image, I don't know how you could make a movie. And so we like it a lot because we can see lots of things with MR. The problem is that we have to wait a long time, and that has serious limitations. So what people try to do is to speed up MR so that it has a wider applicability. And at the end of the week, in the lecture number 8, we'll discuss remarkable progress in this area where now people use compressed sensing for MR pediatrics in a very dramatic way, and I'll discuss this at the end of the week. But for the moment, what we could think about is we have a 500 by 500 pixel image, and it would take a very long time to acquire the number of Fourier coefficients we need, which is 500 squared, which is about 250,000 coefficients. You have to imagine that the time it takes to acquire a coefficient is irreducible because you have to let the spins relax back and forth. That's not something you can speed up. So you have to deal with relaxation times. And so the only thing we can do really is to take fewer samples. Okay, so speeding up MR essentially is sample less. And so here's a little experiment where we're going to look at a sampling pattern in the frequency domain, which goes through along radial lines going through the origin. So in this example, we have 20 radial lines. We have 500 Fourier samples along each line. Okay. And so what we see is that we have, 20 times 500 measurements, which is about 10,000, but we have 250,000 unknowns, so we're missing lots of equations. What's the fraction of equations that we're missing? 96%. So what are we going to do? Okay, so it's a undersampled data problem, an important one. And I'm sorry you can't see this. Here you have at the top, you have the beautiful log and Shep phantom, which you can only guess. Here you've got the sampling pattern in the frequency domain. And what I'm going to show you here is I'm going to take a line through the Fourier transform. Here, I'm going to look at its real part, and that's the blue curve you get to see here. And of course, each time this line crosses a white pixel, it's a place at which I have Fourier information. Okay, so this corresponds to those red dots. Right? So from time to time, I get to see this curve. Right? And my goal is, of course, to recover the in-between samples. And that looks like, of course, it's an undetermined system of equations. I'm sampling the Fourier transform. The problem is the Fourier transform is a nasty object, which is globally oscillatory, and so it seems difficult to find a formula that would actually interpolate between those samples. Okay? So in MR, we have also a very important kind of undetermined system that will motivate a lot of the theory you're going to see, where we observe noisy samples of the Fourier transform. We have a number of samples which is much smaller than the total number of unknowns. And so that is a place in medical imaging where underdetermined systems come up all the time. Okay. Also in the lectures, we're going to discuss a new field. It's the field of matrix completion that is about a different set of questions, but also about underdetermined systems of equations. And I'm going to introduce a Netflix problem. Now in the UK, I don't know, do you have Netflix in the UK? No. Okay. All right. So the Netflix is a company in the United States, but you have Apple computers in the UK, right? Okay. All right. So the Netflix is a company that is essentially renting out movies to users. The company is about 1 million users. They're renting about 25,000 titles. And the thing is that they ask people to rate movies. And of course, they ask me to rate movies. And because I'm lazy, I've rated maybe 20 movies out of 25,000. Of course, I've not seen 25,000, but I've rated 25 movies. What Netflix wants to do, so what we have is Netflix has a data matrix that looks like this. The columns are movies, the rows are users, and each time you see a cross, it's a movie that a user has rated. Okay. What Netflix wants to do, and for obvious reasons, is that they would like to be able to predict ratings for movies that you have not yet seen. And why would they want to do this? Because they want to be able to make money. So if they can provide a good recommender system and suggesting movies you might like to see, they will make money. It's very different from life in Cambridge, where when you go to Cambridge, you go to all bookstores, and the bookkeeper has made sure that the kind of interesting books are nicely displayed. You come in, you see nice books, and you come out and with books that you did not intend on purchasing when you got in. The problem in the US is that we do a lot of our shopping online, and how do you do the job of a nice bookkeeper online? And so what you have to do is you have to come up with a recommender system that would be able to predict your preferences so that they might want to buy things you might like. Okay, so the problem that Netflix faces is to complete the Netflix matrix. That is, it's a very different kind of problem. You see a few entries of a large data matrix, can you guess the entries you've not seen? Okay, and we'll talk about that as well. Okay, now of course this problem has lots of applications beyond the helping companies make money. We'll talk about application in quantum physics of this problem, which I find very exciting. Okay, so the matrix completion problem is something like this. Mathematically speaking, you have a large data matrix. You can only see a few subset of its entries, and your goal is to infer the missing entries. How can you do it? Okay, again, an underdetermined system of equation. Equation is at this entry I have these things, but you'd like to see them all, but you see only a fraction. Okay, so we've seen several instances of underdetermined systems of linear equations of the form b equals ax. And when fewer equations and unknowns, there's a fundamental theorem of linear algebra that says that you cannot solve for x. In fact, I taught linear algebra last quarter, and that's what I taught. If you have fewer than n equations, you cannot recover x. And in general, I want to assure you that this is correct. Okay, I'm not claiming that this is not correct. This is correct. But in practice, we'll see that if I'm allowed to make a very few assumptions about x, then we'll see that we can actually recover x. And the theme for the second part of the talk, which is like convex optimization, yes, I have underdetermined system, but when I invoke convex optimization, it seems to get things right. Okay, so let's visit this theme. All right, so we're going to assume a special structure, and in this talk, structure might mean two things, but in general, it's not difficult to take what's given, what's explained in this lecture, and apply it to other kinds of structure. So we're going to examine two kinds of structure, but there are several others. And the two kinds of structure we examine is, what if the right-hand side is sparse, that is, has lots of zeros and only a few number of non-zero coefficients? What if the right-hand side has low rank? In the Netflix case, it is believable that the Netflix matrix, the matrix of user ratings, is a low-rank matrix. Because, for example, preferences for The Godfather and for Goodfellas are extremely correlated. So the columns of the Netflix matrix are highly correlated. And in fact, if you were to do an SVD of the Netflix matrix, you would find that the singular values become less significant after 25 or 26 or 50, something in that range. Okay, so we're going to see that if we can make some structural assumption about the right-hand side, for example, sparsity or low rankness, then we can often find solution to these problems by convex optimization. Okay, so sparsity is everywhere around us, and for example, it is certainly the case in the first genetics example that if we believe that there are some genes that have to do with high cholesterol levels, they're not everywhere on the genome. There's only a few genes that might be responsible for cholesterol level, and so in this case it might very well be that we can assume that X is sparse because only a few genes are responsible for a quantitative trait. And so we're going to say that a vector X is S sparse, and that's a word I'm going to use all the time from now on, if the number of its components that are not zero is less or equal to S. Okay, so such a vector I'm going to call S sparse. In this thing, there's also another piece of notation, which is the L0 norm of an object. And the L0 norm is not really a norm, it's a quasi-norm. And what it does, it's counting the number of coefficients that are non-zero. What we're going to learn in this lecture is that under some conditions, if I do noiseless recovery by L1 minimization, then it is exact. Okay. All right. So if I have an underdetermined system of equation to solve, and if somebody tells me, look, Emmanuel, the solution to this system is sparse, then I might want to find the sparsest solution that explains my data. And mathematically, I can cast this as an optimization problem where I'm going to try to find among all vector x such that ax equals b, the one that has the smallest L0 norm. That is, I'm going to try to find the smallest number of columns such that the linear combination of these columns gives me b. Right? And if you believe in sparsity, that's what you should do. And you should try to minimize this thing, and the problem is that there's no way I can do this. that it's known to be a combinatorially hard problem. If you can show that you can minimize the L0 norm in polynomial time, then P equals NP. So it's very hard. The best algorithms we have to solve these problems, the L0 problem, do nothing more than try all subsets of columns and try to solve the Ax equals B. So because we're practically minded, we're going to try to propose a relaxation of this combinatorial optimization problem, which is a relaxation that has been used for a while now, where instead of minimizing the L0 norm, we're going to minimize the L1 norm. Okay, so now what is the L1 norm of a vector? I'm sure everybody knows what it is. It's simply the sum of modulus. So the L1 norm is simply the sum of the amplitudes. In many ways, the L1 problem, the mini L1 problem, is the closest convex problem, is a convex problem that is closest to the L0 problem. Why is that? Well, the L0 norm, if I look at the component of the L0 norm, which is essentially the indicator function of xi not 0, so it's 0 if xi is 0, it's 1 otherwise, is a function that looks like this. It's 0 at 0, and otherwise immediately it's 1. So it's a discontinuous function that takes on two values, 0 or 1. Now, I could ask over the unit interval, for example, over the unit interval minus 1, 1, what is a convex function that is the closest to the best lower bound to this L0 norm? Right, so now I have the interval minus 1, 1. I have this function, which is here. I have plus 1 here. I have minus 1 here. And what I want to find is I want to find the tightest convex lower bound. Right? And if I do this, it has to lower bound my function over the interval minus 1, 1. And so what I'm going to get is I'm going to get the absolute value. Okay, and similarly, the L1 norm is the tightest convex lower bound to the L0 norm over the cube, over the unit cube. So in many ways, the L1 norm is the closest thing you can get to L0 maintaining convexity. Another way to say what I'm just saying is that if I look at the set of sparse vectors of that are one sparse, which are full of zeros, except in one coordinate either plus and minus 1, and I look at their convex hull, that is the closest convex set that contains them all, that contains one sparse vectors, then what I discover is that it's the L1 ball. So in all these senses, if you try to find a convex formulation of an L0 problem, which is as tight as possible, then you'll end up with the L1 norm. Okay. And so now the good thing about the L1 norm is that now minimizing the L1 norm, since it's a convex objective, it's a norm after all, so it's a convex objective subject to linear equality constraints, it's actually a convex optimization program, which is a very simple optimization program. It's simply a linear program. So let me explain this in a minute. Suppose I want to minimize the sum of the absolute values of xi subject to Ax equals b. I can introduce what are called slack variables, ti, which are essentially the absolute value of xi. Okay, and I want to minimize the sum of ti subject to Ax equals b under the constraint that the absolute value of xi is less than ti. So, of course, minimizing the L1 norm will be the same as minimizing the sum of ti's subject to Ax equals b, and xi is less in absolute value than ti's. Okay, so that's completely equivalent. Of course, saying that xi is an absolute value is less than ti is the same as saying that xi is between minus ti and ti. And therefore, minimizing an L1 norm subject to Ax equals b by introducing this slack variable t, what I can do is I can reduce this to a linear program, because what I have to do in these variables x and t, I have to minimize a linear function of t subject to linear equality constraints, Ax equals b, and linear inequality constraints x less than t and x greater than minus t. So if I have an LP solver, this is something I can use. Traditionally, people would solve these problems with a simplex algorithm, which for the scale of problems of interest to us is not applicable, and so we'll discuss this in lecture 7. Okay, now if I have noise, then I can try to minimize the L1 norm subject to relaxed constraints because I don't want to enforce too much of data fidelity since the data is not accurate anyway. And so I might want to minimize the L1 norm subject to a relaxed fit where maybe the distance between B and AX is not too big in any different norm you like. And what we'll see is that under some conditions, if you have undersampled data that are not only undersampled but also noisy, we'll get accurate recovery provided that the noise level is not too high. And perfect recovery if the noise level is 0, that is Z equals 0. All right. Okay, so I want to show you now, because I said at the beginning, it's important for me to tell you where we're coming from, because we're not the first one to use the L1 norm. I want to show you some pioneering work in the use of L1 norms. And this work is motivated by real problems, which I'm going to discuss now. I think the first industry that really looked at the use of L1 norm in a systematic way is the oil industry. People interested in knowing what the upper crust of the Earth is made of. So what is the problem of interest in reflection seismology? So I'm going to, in very, very broad terms, I'm going to discuss reflection seismology, and I'm only going to sketch it, of course. The goal is to know what the Earth is made of. And to do this, of course, if you work in the oil business, you care about what the Earth is made of because you want to know where is the oil. And now how are we going to sense the Earth's upper crust? Well, you could have what is called a seismic exploration, where you have a boat going at sea. And what this boat is going to do is going to create explosions. So it's going to send acoustic waves down the Earth. And basically, these waves are going to be reflected. And so you're going to collect the echo. And out of the echo, you try to infer what the Earth is made of. That's, in principle, that is as simple as this. Right? So what you do is you create an explosion. So you beat the sea with a hammer. So boom, you have an explosion. The acoustic wave propagates down the Earth. Then, of course, as you're propagating down the Earth, you encounter different materials. So maybe you have water, sand, oil, stuff like that. Each time you have a discontinuity, you have echo coming back. You collect the echo, and out of the echo, you try to know what the Earth is made of. Okay? The properties of this material are going to be reflected by this impedance function AZ, which is a property of the material. And if we assume that the Earth is fairly homogeneous except for these discontinuities, it would be a function that is essentially piecewise constant that changes value as you're crossing different types of material. Now, mathematically, how does an experiment look like? Well, you have, if we were to do things in 1D, where I just propagate things down the z-axis, of course, it's in general in 3D, but let's say for simplicity, we're propagating down in 1 dimension. Then we have the acoustic wave equations, which I'm sure everybody knows is of this form. Okay. So in this equation, that's the acoustic wave equation. In this equation, time is t and depth is z. And what is u? What is the ut of z? It's a particle displacement at time t and depth v. That's your acoustic wave. Az is the acoustical impedance. That's what you would like to know, because if you knew this, then because you can go back to your table, and if you know at what depths, what kind of impedance you have, you know, oh yeah, well, here I've got water, here I've got sand, here I've got oil, and so on and so on. That's what you would like to recover, this impedance function, because once you have it, you go back to your table, and you know the impedance of the various materials, so you would know what the Earth is made of. Okay. So now, what kind of data is a seismic experiment is going to generate? Well, I said you hit the surface of you send an acoustic wave, which means that you control the boundary conditions of this differential equation, and you're probing the system with what's called a wavelet, and so you're controlling the boundary conditions. So what you have a wavelet f of t, which corresponds to the displacement at the sea level z equals 0 at time t, the derivative in the z direction. Right? That's what you control. What does it mean to listen to the echo? It means that what you can measure is you can measure the displacement, the derivative of the displacement with respect to time at the sea level. This is a function h of t. That's the data that the microphones trailing the boat record. So you create explosion, you get back the echo, and out of this pair f of t, ht, your problem is to find impedance. That's a very difficult problem because the relationship of the unknown A is not linear in the problem data. Okay, so what you've got is you've got a system like this where you have your wavelet probe, something like this, and then that's f of t, and h of t, which is a seismic trace, what you record, looks something like this. And out of this seismic trace, you would like to read the impedance A of z. Okay. So the relationship between the problem data and impedance is complicated, but we're going to make the story simple. And what we do when we don't know how to solve a nonlinear problem, we linearize it, and that's what people do. So we can assume that impedance is a constant function plus a small perturbation, alpha z, and the derivative of alpha is called the reflectivity profile. And so if I have a piecewise constant impedance, alpha prime will be a bunch of Diracs, a bunch of spikes, corresponding to the locations where I have discontinuities in A. Now you do some math, which I'm not going to do here. You do some mathematics, and what you realize is that with this approximation, the problems becomes much easier. What you've got is you've got a function g of t, which is a sum of what you send in plus what you collect. So the sum of input plus output is related to what you're looking for, that is a reflectivity function, through this convolution equation. Right. So you can measure g of t, which is what you put in plus what you collect, is equal to the convolution between the reflectivity profile, which is what you see at the top, with the probe f that you're sending in. So to recover the reflectivity profile alpha, or alpha prime, what you need is you need to solve a deconvolution equation. Okay, so what I can write down is I can write this equation as g, which is observed, is equal to the convolution of r, which is the reflectivity function times f, the convolution between the probe f and the reflectivity function is equal to g, and that you have to solve a deconvolution problem. So it looks very much like the microscopy example we've seen before. The problem is that you cannot excite the medium at all frequencies. So the wavelet you can send in is band limited in nature. You cannot excite low frequencies and super high frequencies. So the probing wavelet is band pass. And so if I were to plot the Fourier transform of your probing object, it looks like this. It cuts out the low frequencies, it cuts out the high frequencies, it only lets through a few frequencies. And so your seismic experiment is missing all of its low and high frequency contents. But that's a problem in your deconvolution problem, because the unknown is something like this, and this has lots of high frequency content. In fact, it's a high frequency object. And yet you don't get to see the high frequency objects. Okay, and so that's the problem that the seismologists are facing, that they have bandpass data to recover actually high pass objects. Okay? And so of course it's a deconvolution problem, and I can cast this in the Fourier domain, where deconvolution problem in the Fourier domain is simply a multiplication problem. So I get the Fourier transform of the observed data is the Fourier transform of the wavelet times the Fourier transform of the reflectivity function. I would like to divide by f hat to be able to recover r hat, but I can't because f hat vanishes. Okay. So I have lots of missing frequencies or equation, and this is very much like the microscopy example. Okay, so the fact that the Earth is irregularly layered means that our reflectivity profile is 0 in lots of places and non-zero in the places at which I have discontinuities, and so I have a sparse unknown. All right, and I think in a very influential paper, John Claerbout and Muir in 1973, and just showing you how far back these L1 methods are, John writes, perhaps the L1 norm can be utilized to give an output trace like figure 13, because everything that people were using in geophysics when they were working on deconvolution problem were producing things that have nothing like what you're looking for. In fact, he said, in deconvolving any observed seismic trace, it is rather disappointing to discover that there is a non-zero spike at every point in time, regardless of the data sampling rate. One might hope to find spikes only where real geologic discontinuities take place. Right? And people were doing like minimum energy type deconvolution were getting essentially garbage. And what John suggests is that maybe we can use the L1 norm to produce an output that looks like the output we're looking for. And that's a very early use of the L1 norm. Now, these ideas have been crystallized in the literature in geophysics. And if you look back at late 1970s, mid 80s, what you would see is you'd see a lot of proposals based on the L1 norm. The first proposal by Taylor, Banks, and McCoy, if I write my convolution equation, it's just matrix notation, G equals FR, suggests to find a reflectivity profile R that minimizes the sum of two objectives, the one norm of R, and of course a data fidelity term, which is lambda times the distance between what has been measured and what you would get if you were to use this profile R. A few years later, Santosa and Symes said, well, we suggest something else. We like the L1 norm, but we want to change the fidelity term in an L2 squared norm. Okay, and so what you could see in the literature of geophysics is lots of proposals trying to fit undersampled data with L1-like criteria. Okay, so when you look at these proposals, which are of the form RL1, the L1 norm of R plus a data fidelity term, Santosa and Symes that the L1 norm forces solution to have small L1 norm, and what they observe is, of course, it constructs a solution with the least number of non-zero components, that it has this tendency of outputting sparse spike trains, which is what these geologists want. And the other term is, of course, a goodness of fit criterion, and we can argue about which one is best, but the point is that the use of the L1 norm to actually produce sparse spike trains. And so what did these people observe in this community? They observe that if we have band-limited data that is noiseless, and if the unknown reflectivity function is a sparse spike train, that is, you're trying to solve a deconvolution problem, which is very severely ill-posed, but you make the assumption that the unknown is sparse, then what Santosa and Symes found is that the use of minimum L1 criterion produces, under many circumstances, a correct solution. And they're not the only ones to have found these things. There's a large literature in geophysics explaining that, yes, indeed, when we run experiments, numerical experiments on the computers, that's what we tend to see. Okay, so that's kind of the early use of L1. But yet, from some reason, the use of L1 methods did not pervade the sciences at large. In statistics, L1 has been reintroduced as the lasso, and in computational harmonic analysis, people started to use L1 in the form of an algorithm called basis pursuit to deal with over-complete representations in a way that I will explain. So if you are growing up like me, studying computational harmonic analysis in the 90s, it's a field that tries to find bases that are good for representing several things. And so it's a very active field of research of people trying to commit themselves to finding good representations for scientific phenomena of interest. And it's a field that has developed the wavelets, time frequency basis, ridgelets, curvelets, and so on. So people were trying to find representation that provides sparse representations of functions of interest. By the late 90s, it was an emerging feeling that there is no, or mid-90s, that there is no universal representation, that several representations have their own targets, things for which they're good, and things for which they're not good, and that somehow you would want to combine them. Like you would not want to use wavelets alone, but you would like to use wavelets and curvelets, or Fourier and wavelets, not one single basis all by itself. And best means that you could get sparser representation by combining all of these bases. So there was a very influential paper in '93 written by Stéphane Malat and Stephen Zhang, where they said, okay, well, suppose we have several orthobases that I'm going to label phi 1 through phi d. I can concatenate them, I can put them together and create what they call a dictionary, which has many more columns than rows, because now you assemble orthobases together. And now, of course, you're going to have a way of expressing every signal as a superposition of basis elements taken from these multiple bases. But of course, now the decomposition is not unique, because you have dn columns and only n rows, so you have many such decompositions. And which one should you take? Well, you should try to find the one that is the sparsest. That is, you should try to find a decomposition that has the fewest term and reproduces your signal. But of course, we can't do this. We argued that this is NP hard. And so in complete analogy with what people were doing in seismic, you cannot solve L0, so let's solve L1 instead. And so Shen, Donohoe, and Saunders proposed a basis pursuit which replaces the 0 norm by the 1 norm, but otherwise do the same. Okay, in complete analogy to what they were observing in the world of seismics. Now, why would we want to do things like this? Suppose you give me a noisy image Y, which is possibly noisy. I would like to perhaps decompose it as a superposition of two images with different content. So this is the work of Jean-Luc Stark and his colleagues in France. And so, for example, we could have several examples, like I have an image that contains geometric information and texture information. I would like to be able to separate the geometric content from the texture content. Or it works in cosmology. I have pictures of galaxies, and I would like to separate what looks like isotropic structures from what looks like filamentary structures. And Jean-Luc Stark's idea is to say, well, let's find representations that are good for geometric structure, for texture structure, like, for example, a local Fourier transform in this first example, and perhaps a curvelet transform for this one. And here, like, wavelets are good for isotropic structures, curvelets are good for filamentary structures. And let's try to find sparse expansions in this combined dictionary. And then I look at the wavelet component, maybe it's going to be wavelet-like. And when I look at the curvelet component, it's going to be geometric-like. And then maybe I can achieve separation this way. And now I'm a bit worried about how much you're going to see. But if you subject this algorithm to images that are superposition of cartoons and texture, by looking at the curvelet component, you'll get exactly the cartoon. And by looking at the Fourier component, you'll get the texture. So the top picture superimpose the texture on top of a cartoon, and automatically, by finding the sparsest expansion in a combination of curvelets and Fourier, you would separate the cartoon part from the texture part. But obviously, you can't see these images very well. So what is done is like you can't see anything. Okay, so maybe I'll skip this, which is a good thing to know for future lectures. So here it's an example where you separate lines and segments from points, but for some reason it's not showing.
Just try turning the front lights off. One's directly above you.
Okay, well, I don't know. I mean, maybe at the end I'll try to. Okay, so for those of you who are interested, there are beautiful pictures where we see faint. The whole point is that these lines are faint and buried in noise, but when you look at the ridgelet part, it pulls out the line, the wavelet part puts out the dots, and then the residuals is just noise. Maybe, I don't know. Okay. All right, and then you can run this on cosmology data and get isotropic features and filamentary features. And so people like to combine these representations. Okay, all right, so now what did we know prior to compressed sensing about L1 recovery? People witnessed empirically that it returns sparse solutions. What did we know? And so I would like to present some early, very important results showing you that, of course, there is a literature that precedes what you're here. I think the first striking result is due to Ben Logan, who is a harmonic analyst. And his result was actually written in his master's thesis in 1965, and it is a very interesting mathematical result. So let's look at this result. He says that we have a band-limited function, that is a function whose Fourier transform vanishes outside of a frequency interval of length 2 omega. Right, so I have capital omega. The Fourier transform vanishes after the frequency cutoff, capital omega. I observe this band-limited function, but on top of it, I have what we call impulsive noise. Right? So I observe F0t pretty much everywhere, except from time to time, I have this impulsive noise, which is supported on a sparse set capital T. Right? So impulsive noise looks like this. Yeah, I don't know where it occurs, but it's impulsive, so it occurs rarely. Okay. I have impulsive noise. It says to recover the function, like getting rid of this impulsive noise, of course, the underlying object is quite smooth, right? So you see a smooth function plus impulsive noise. So it doesn't seem to be a problem that is at least not too hard, because while you look at a smooth function plus impulsive noise, you may think that maybe there's a hope. But the brilliance of these results says, okay, to recover the band-limited function, I'm going to try to find a function f which is closest to what I've observed in an L1 sense. Now it's the L1 over the whole real line. Okay? So the recovery is very simple. Take the data, find that f which is closest to the data in an L1 sense. And the striking result is something like this. That is, if the set is a Lebesgue measure of the set of points that have been corrupted times the frequency cutoff is less than pi over 2, then what Ben Logan could prove is that this solution is actually exact, that you actually get rid of the noise exactly. That holds whatever is the function in B omega and whatever the size of the noise is. It's always true. Okay, so what it says is like it starts to explain some of the mystery associated with L1, that says that I minimize this distance in an L1 sense. I try to find the band-limited object that is the closest to y in an L1 sense. And what Logan can show is that if I make strong assumption about the noise is not too widespread and the function is band-limited, and if the product between T omega is less than pi over 2, then I can guarantee that the recovery is exact. Okay, so 1965. Now, what is the connection with what people were doing in geophysics? Geophysics is, well, F0 band limited means that F0 is sparse in the frequency domain, right? It only has low frequency component. You know, it is very sparse in the frequency domain. What is the equivalent of undersampling is that it's undersampled because whenever the noise is not 0, you're missing information, and so that's a connection with people, the work of people in geophysics, right? So F0, assuming that F0 is band limited, means that F0 has some sparsity in the frequency domain, and therefore things might work. And indeed, they do work in a strong mathematical sense. Another result that I like a lot is directly applicable to the seismic experiments that we've discussed before, which is that now we have data y, which is a convolution of a sparse spike train and our convolution kernel k, which unlike the frequency experiment where you miss both low and high frequencies, it's just it's a high pass kernel that kills frequencies below pi. Okay, and F0 of t is sparse in the time domain. Now we're going to make an assumption about the sparsity of t. We're going to say that F0 of t is 0, so it's sparse, so it's a lot of time it's 0 if t is not in a set t. And then I'm going to make an assumption about the density of t, that how much mass can t put in every interval of length 1. So I have an interval of length 1 between t and t plus 1. Over there are portions where f of 0t might not be 0. But what I want to make sure is that the fraction of time per unit interval, that f0 of t is not 0, is less than 1 over pi. So what that means is that any interval of length 1 is occupied only 30% of the time, roughly. So let's make this assumption. We have a high-pass kernel that kills all the frequency below pi. we have an object which is sparse in the time domain. And what did Donohoe and Logan prove? They proved that the minimum L1 solution of Saint-Lausanne-Symes is also exact. That if I could minimize the L1 norm of f, subject to the data I have, then they can guarantee that the solution is actually f naught. Right? So what this theorem says, it says if I have an object which is sparse in the time domain, and sparsity means it could have some low frequency component, of course, but sparsity means that 30% of the two-thirds of the time it's 0 or something like this, or 70% of the time it's 0, 30% of the time it's not 0, in a very equidistributed fashion, since for every interval I need to have this condition. And I observe only high-pass data, then I'm killing all the frequencies below pi. It doesn't seem to matter because I can get the low frequencies by solving an L1 problem. Finally, another beautiful results coming from the third string of applications I was discussing before, which is applications to basis pursuit. So here we have two orthobases. So we have phi 1 is an orthobasis, and phi 2 is another one. And we suppose that we're going to make a signal which has a sparse linear combination of columns from phi 1 and columns from phi 2, and we would like to recover this sparse combination. So for example, let's assume that phi 1, for example, is the identity, and phi 2 is some Fourier transform. Then we're going to make a signal which is a superposition of a few columns of the identity. So this is going to be a signal which is a sparse in time, and a signal which is a superposition of a few columns of the Fourier transform. So we're going to have a mixture of a signal which it's a sparse signal in time plus a sparse signal in the frequency domain. And the question is, you give me the sum of these two, can I find the time signal and the frequency signal? Okay, and that's been studied by all these people on this slide. Okay, and in this general setup, there's a notion of coherence that was developed by these researchers, which looks at, so I look at all the columns in phi 1. So these are two orthobases. So phi 1 is an orthobasis. Phi 2 is another orthobasis. And what I'm going to do is I'm going to look at all the dot products between columns of phi 1 and columns of phi 2. And I'm going to look at the maximum of this. This is something that people call the coherence M. Okay. So I look at the maximum correlations between columns of phi 1 and columns of phi 2. And because these are two orthobases, I have Parseval lurking in the background, which means that this correlation cannot be less than 1 over square root of n, because some things have to sum up to 1. Okay, now I'm going to give you a signal that is a sparse superposition of columns of phi 1 and column of phi 2, and I'm saying, can you do sparse recovery? And so in a beautiful paper, Michael Elad and Freddie Brookstein proved the following. They proved that if you give me a signal which is made of a few linear combination of columns of phi 1 or phi 2, and what does it mean, a few? It means that the number of non-zero coefficients has to be less than 1 over the coherence, so quite small, so less than square root of n. Then there's no other sparse explanation of it. Right, that if you were to solve L0, you would find it. What they also showed, which is more remarkable, is that if the norm is less than 0.91 divided by n, then you will get it by L1. Right? So what the theorem says, it says I have two bases. For example, I have superposition of sinusoids and spikes, and I want to recover which time samples are associated with Diracs and which frequencies are associated with Diracs. In this case, the coherence is square root of n. And so what Elad and Brookstein tell us is that if I made my signal by adding fewer than 0.9 square root of n Diracs and sinusoids, and I solve L1, I will be able to find those coefficients. And so what this says is if f has an extremely sparse expansion, then basis pursuit will find it. But it's extremely sparse. Square root of n over something. All right, so now I'm done with this kind of history of L1 and some early result that I find extremely striking and that was, of course, very much on our mind when we started to work on this theory. So now, what is compressive sensing? Okay, so first the name was coined by David Donahoe. It's a big field today. It has become a label for sparse signal recovery. So people call compressed sensing everything. Like if you have sparsity underdetermined, they call it compressed sensing. It has become a label for sparse signal recovery, but it's really one instance of underdetermined systems of equations. It really informs analysis of underdetermined systems. It really changed our viewpoint about underdetermined systems, and by now it's a very huge field. And I looked at the number of papers published in this field yesterday, and you have, I don't know, thousands and thousands of papers are published in compressed sensing each year. And so there's no way in these lectures I can give you a sense of all that is done. I can only give you an overview of what people do. And there are lots of people working in this field, and what's great from my perspective is we have pure mathematicians working on compressed sensing, we have applied mathematicians and statisticians working, we have computer scientists, information theorists, engineers, real hardcore engineers who build systems. And so it's great to see an area that is so interdisciplinary in nature, where at the same conference you can see, I don't know, Terence Tao and a circuit designer. Okay. What is at the heart of compressed sensing is a paradox, and the paradox is very simply stated, is something like this, that we are spending a lot of time and money building sensors, knowing very well that whatever we measure, we're going to throw away. And that's a fact of life. Here is a picture of my backyard. So this is acquired by a very old camera. This picture was taken a while ago. And I have probably not many sensors, like maybe 2 megapixels. That's why this file is 5 megabytes. Today, it would be 100 megabytes or more if you have a 20 megapixel camera. This is a raw data before the camera does anything. And then, of course, we subject this data to a compression stage, and that's the data where you have the same picture stored by JPEG, 150 kilobytes. You throw away 99% of the bits, if I can speak like this, and it's difficult to tell the difference. In fact, if I were to give you both these images and say what is the uncompressed one and what is the compressed, it would be a little bit of a test. So now so we have massive data acquisition. What's problematic is we design all these sensors knowing that most of what they're going to measure we're going to throw away, and so it seems extremely wasteful. This state of affairs has been most brilliantly captured by David Brady, who wrote a book on imaging. He's an optical engineer at Duke, and he wrote this beautiful thing that I find really capturing the essence of what's going on. One can regard the possibility of digital compression as a failure of sensor design. If it is possible to compress measured data, one might argue that too many measurements were taken. And that's exactly the state of affair we live on, which is we buy all these sensors, they collect data, and then we throw 99% away. And we know, it's not that we say, oh, we were not smart enough. It's like, it's different. It's like we know ahead of time that we'll throw most of it away. In fact, that's why my camera runs out of power, by the way. A digital camera runs out of power. What are the two main sources of power consumption in a digital camera? The LCD screen, that's the main source of power consumption, and I don't use it because I don't like to have to recharge my camera all the time. Second, this compression algorithm, because to crunch numbers, to perform the CPU, to crunch numbers, to do data compression inside the camera, you need computer power. You need to crunch numbers. And that's why I run out of battery, not because I take pictures, but because I compress them. Okay, so this is a long-established tradition where we sample like crazy. It's almost, I've heard people say it's a staple for a society. Massive consumption followed by massive dumping. So we sample like crazy, we compress, we throw away most of it because that's what we need to do to transmit or store information. Okay, and so at the other end of the spectrum, we receive data, we decompress, and so on. And so the fundamental question that one can ask is it possible to acquire just a useful part of the signal and not the part that you'll throw away? Okay, so there are two premises in compressed sensing, that you can exploit sparsity when acquiring signals of interest. That we're going to lecture a lot about this. So that's the premise, is that signals that we wish to acquire are sparse or approximately sparse. Approximately sparse signal, we're going to call them compressible. And that it is also possible to condense information in a sparse signal into a small amount of data by means of incoherent projection, which we're going to explain what this means in a minute. Okay. But basically, compressed sensing, it says if you know that you're sensing a sparse signal or an approximately sparse signal, you can design a non-adaptive sampling scheme that will make just few measurements about this signal, and these few measurements hold all the information you ever will need to know about this signal. Okay. So I need to explain sparsity, but sparsity we've seen in great detail, but let's look at it in the context of image processing, for example. Here we have a megapixel image, which is not at all sparse, because a sparse image would look like the sky at night, which every pixel is black, except I would have a few white dots corresponding to stars. This is not a sparse object in the time domain or in the spatial domain, but if you look at it in the right basis, it's becoming sparse. So this is the same object, but viewed in the wavelet domain. Okay, and when I look at the wavelet coefficient of an object like this, what I get to see immediately is that a few coefficients are large, many of them are very small, and so I have a picture that looks like this, where it seems that very few coefficients actually capture most of the energy in the object. Okay, so I have some form of sparsity. When I look at the histogram of coefficients, I see enormous concentration around 0. And of course, this is what allows image compression. So if I'm going to do an experiment to just drive this point home, but suppose I compute 1 million wavelet coefficients of a megapixel image. So I'm going to mimic what kind of my camera does. Of course, my camera does something more complicated, but for the sake of it, let's just present it in the simplest possible term. I acquire 1 million pixel values. I compute the wavelet transform. I don't even bother to store the small coefficients. I'm going to keep the largest 25,000 coefficients. So in this plot, I'm going to set to 0 all the little guys. I'm going to keep the large guy. I'm not going to encode them. So I'm going to reduce file size by an enormous amount because I'm going to throw away 97.5 of the coefficient, and I'm going to invert the transform. So when you do this, well, you get the picture on the right. And again, it's difficult to tell me which is which. And what we discover through this simple experiment is that image compression works. And this principle is what underlies modern lossy coders, that everything you do lossy compression on these days, sound, still picture, video, is essentially based on this principle. Take a data set, transform it so that you have near sparsity, don't bother to encode the small coefficients, encode the largest one, that's your compressed file, and then if you want to read it, just invert the transform. That's what your web browser does, that's what everything I'm aware of does. Okay, and so of course, whenever you have a representation in which you have sparsity, then you're in good shape, because what you take is you take an input image, you compute a transform, and then you're going to quantize the coefficient, and you're going to encode them with some kind of Huffman code, if you will. And the thing is, you have very few things to encode, because after the transformations, many coefficients will not pass the quantization level, so they don't need to be encoded. Okay, so that's what makes data compression work really. Okay, so now we want to go back. We want to explore the main theme of these lectures, which is something like this, which is, okay, so let's say I have a sparse signal that I wish to sense. Okay, all right, so let's say I have a signal that has some sparsity pattern that looks like this. Of course, I don't know the locations of the coefficients that are not 0. I don't know the amplitudes. What I'm asking is, can I actually take measurements about this object in a non-adaptive way? That is, I don't want to play the games of 20 questions where I ask, is this a man? And depending on the answer, I adapt the future question. I want to be I don't want to be adaptive. I want to be non-adaptive because I want to have a very simple sensing scheme to implement without feedback. So I want to take non-adaptive measurements. So that is, I want to design sensing waveforms and design sensors that all what they do is they correlate X with AK. And so then I'm going to make measurement called YK. And what we're going to propose we're going to propose lots of, we're going to see in lecture 2 which measurement we would want to make, but let's say for the simplicity of this lecture, let's assume that the AKs are white noise. That is, that I'm going to try to calculate that the sensor, what does the sensor does, it takes an inner product between X and AK of T, which is white noise. So it looks like something like that. It's white noise. So it sounds completely silly. What you do is you correlate the object with white noise, and you get one measurement, and then you take another independent copy of white noise, and you correlate the object with its copy, and then you do this a few times. And then you get an underdetermined system of equations like we've seen, and you reconstruct by L1, which is things we've discussed already. A fundamental result is this, that if you take a number of white noise samples, which is roughly the number of non-zero coefficients times the log factor, log in the total dimension of the signal, then this will work. That is, that when you actually take S log n measurements that simply correlate the signal with white noise, and you reconstruct by L1, then you get the exact signal back. Okay? And so what I'd say is, like, if I'm about to sense a sparse signal, the terrible thing would be, of course, to suppose this is a signal in, these are arrivals of things. The terrible thing to do would be to sample it in time, because I would spend my life sampling zeros, and so of course I could not afford to actually even jump over a sampler, because what if there's information at the next time? But what we're going to see is that if we actually take random correlations between the signal and white noise, and we solve by L1, then this recovers the signal exactly. And what it says is that efficient acquisition is possible by non-adaptive sensing. Right? You can efficiently acquire objects which are sparse by taking very few number of measurements, how many, essentially proportional to the number of non-zero coefficients, and reconstruct by optimization. Okay, so the picture is this. We have a local signal which lives here. We have Gaussian measurements waveforms that look like this, incoherent waveforms. The signal is local, the measurements are very global. So in each measurement, there's a bit of information about each signal amplitude and their location. And what L1 does, it teases information apart to actually recover the location where the signal is not zero and their amplitudes. Okay, in fact, in real life, of course, signals are never exactly sparse. They're always only approximately sparse. And so an image like this is never exactly sparse. And what happens, and whenever people give talks on compressed sensing, is, yeah, but what if I'm not sparse? Right? So what if, you're sampling at a given rate, but the signal is actually not as sparse as L1 would like it to be? What happens? And so that's kind of what I try to tell them, is that, well, in real life, signals are not, they're never really sparse. So now, of course, I would like to sense an image like this. This is a wavelet coefficient table. Of course, locations indicated by bright yellow dots are locations in the wavelet tables where coefficients are large. So you see most coefficients are very close to zero, except along things indicated by the geometry of this cameraman. And so a priori, of course, I have no idea what to measure. Okay, so we're going to use this non-adaptive sensing mechanism by just correlating this image with 2D white noise, for example. Okay, and so what is the view of the world? The view of the world is the classical viewpoint, which I've explained at the beginning, is, of course, you measure everything. So you measure all the pixels, all the coefficients, and then you perform compression. That is, what you do is, let's say the experiment I've shown you before is that you take all the pixels, you look at which coefficients in your favorite basis carry the most information, are largest in amplitude. You store this, you discard the rest. So you have this blue signal and this red signal, which is the best sparse approximation that I can get by only using S non-zero coefficients. This we're going to call XS. So the definition of XS is very simple here. It's going to be the argmin, that the signal which is closest to X in an L2 sense, for example, but has to be sparse. That's my definition of XS. It's the best S sparse approximation to the signal, which I would get if I had an oracle, would tell me, Emmanuel, I've seen the signal, I know where the big entries are, and I'm going to just give them to you. So why don't you just go out and don't spend your time measuring 10 to the minus 80 because I've seen where the big entries here. Here they are, go out and measure them. Okay? So in this view of the world, you measure everything, you compute your coefficients, and you keep the largest, which is this guy, and then of course you make an error, which is a difference between your original signal and its best approximation. In the compressed sensing view of the world, what you do is you say, no, I'm not going to do this. I'm going to take random measurements. That is, I'm going to acquire information by correlating the signal with these Gaussian waveforms, AK, and I'm going to reconstruct by L1 minimization. And the second fundamental result, which is a result that is mathematically correct, is this, which is that if I take a number of samples which is bigger than S log n, or even I can do better than this, I can say that the number of the samples I need on the compressed sensing side is S log n over S, then when I perform this L1 reconstruction, I have a distortion which is smaller than what I would get by seeing everything and selecting the best bits. And how many samples do I need? I need to get a number of samples which is awfully close to the true number of coefficients that the best compression algorithm would store. Okay, and so what this is like what really is like, that's the story of compressed sensing. What it says is that you can do simultaneous non-adaptive acquisition and compression. You can actually, if you give me a signal which may not be sparse, it's arbitrary, and if you had a system that measures everything and keeps the S largest coefficients of X, you would get a distortion. We can get the same distortion by essentially sampling the signal only a few times, solving an L1 problem. Right? And so if the signal is approximately sparse, if it depends on a number of degrees of freedom, which is very small, so that this error is small, what it says is with very few views of the signal, you get a perfect picture of what it looks like. Okay, so that's compressed sensing. So just take incoherent measurement, non-adaptively reconstruct by L1 minimization, and you're guaranteed to have something which is comparable to the best distortion you could get if, at the end of the day, you decided to keep the S largest terms in X. Okay, we learned through this course that we cannot do essentially better with fewer measurements, that it's not possible, that these mathematical results are within constant tight of, you could not improve them. That is, you cannot come up with a better sensing scheme, even if it could be adaptive. That is, even if you were learning what the signal is and actually updating your sampling as a function of you learning what the signal is made of, we learn in this course that we cannot get the same performance with fewer measurements or with other reconstruction algorithms. But if I allow you to change the measurement mechanism, allowing it even to be adaptive. That is, as you learn, like what you do when you do PD, you learn the solution, and learning the solution tells you what you should do next. That if we play this game, you cannot improve the result you've seen before, and if you don't believe in L1 because you think that there's something better than L1, then again, mathematically speaking, you cannot do better. Okay, so in a nutshell, compressed sensing is a situation in which we can recover a super resolved signal from just a few sensors. What I find really remarkable about this is that the sensing is non-adaptive. It's like what I wrote one day. It's like people hearing without listening. Like your sensor is just hearing. It's not trying to understand what you're saying. It's not trying to understand what the signal is made of. Just take random projection and reconstruct by L1, and the first papers were published at least about 5 years ago. By now, it's a very rich mathematical theory. We'll explore some of it. And compressed sensing, well, we did some work with Terence and Justin, and of course, very important contributions by David Donahoe at the same time. Okay, so this presents us with some opportunities, which whenever measurements are expensive, we'll see applications of this, or they're slow, we've seen applications, or are just simply beyond current capabilities, and we'll see also other applications, or are wasteful or missing. Then maybe this theory offers a way out. Maybe. It's not always that it does, but sometimes it may be helpful. And so we'll explain some of these applications in future lectures. What I will try to convey to you is that these ideas are already making their way into hardware and real applications. So people are building new optical devices, and I'll say a few words about this. People are building new digital circuits. to actually create analog to digital converters that are sampling below the Shannon rate without much information loss, provided, of course, that what they're listening to is structured. People are using this in MR. So there's lots of applications that I hope to be able to develop in future lectures. Okay, so my plan for the coming lectures is to introduce you to theoretical and mathematical ideas, and so that will occupy it for a while. And then, as you've seen, all of these methods relies on our ability to solve large-scale optimization programs, and this is a field fueled by compressed sensing applications that has experienced tremendous growth in the last 5 years, and I would like to review progress in this area and tell you at which speed we can solve these problems on the computer. And then in the last lecture, I want to show you some headway that people make in building hardware based on these ideas. All right, so this is it for the first lecture. As you see, there was lots of precursory ideas in the literature, especially in seismic, about the role played by L1, by the importance of sparsity, and of course, we're going to build on this. Thank you very much. So I do questions, or we don't do questions? Or
If you'd like to.
What's up to you?
Are there any questions for Emmanuel?
So the two theorems or the fundamental results you mentioned, there was some randomness. So the result hold with quality 1 over your random matrix.
Oh, yes. So this we'll see heavily in lecture 2 and 3. Yes. So this is why we have lecture 2 and lecture 3, to explain these results and what they say. And these results are much broader than what you're seeing here. Because in real life, people don't really sense things with Gaussian matrices for reasons that I will explain in details. Let's look at one result, for example. This result? Yeah, so this result is correct, and the probability that it fails is exponentially small in M, in the number of measurements. So what the theorem says is that this is the strongest result we have. I mean, Alain might contradict me, but this is the strongest result we have. If we use a Gaussian measurement ensemble, and I take S log n samples, then I can recover every S sparse vectors, and the probability of failure is exponentially small in M. So if M is 1,000, it's exponential minus 1,000. So for our practical purposes, it's deterministic.
What the constants?
It's like the same probability as, like, maybe you'll find myself tomorrow in Paris by quantum effect or something like that. Yeah, so it's exponentially small in M. Yes.
How sensitive is the overall theory to knowing S?
Well, there's nothing that requires me knowing S, right? Look, all I do is, like, you give me data. I mean, these are very good questions, and we'll spend a lot of time discussing them. But you give me data, and all I do is this. There's no S in this formulation, right? So I can do this no matter what the signal is. Now, what the theory says is that sometimes I'll do well and sometimes I won't do well. So let's go back to the theory. The theory says, if your signal was actually S sparse, then I can guarantee that the recovery error would be 0. Okay, so that's good. But you say, but what if it's not sparse? Well, what if it's not sparse? I can guarantee that the recovery error is the best, the error you would make by approximating the object by its best S-sparse expansion, by its best sparse approximation. This might be small or this might be large. That depends. You know, if we're sensing an object which is complicated and you give me 3 measurements, that's going to be large. But that could be small. Right? So for example, let's go back to our example. This example. Like, what does this example say? It says, we see that with 25,000 coefficients, it's pretty good, right? So what compressed sensing says is takes this 25,000, multiplies this by log n over 25,000, which is 4 or something like that, right? I can get you a distortion which is better than this, the distortion between this and this. Okay. Now, if you say, aha, but 25,000 times 4 is 90,000 or 100,000, I want to know how well I do with 20,000. Well, how well I do with 20,000, it would be the distortion between this and the image I would get by zeroing out all the coefficients but the 5,000 largest, and we have to see whether we're happy with this. There's nothing I can do on that front, right? I mean, what I can guarantee is I can say, if you had a given number of bits to compress, well, I'm going to stick to what I just said, which is like, if you knew ahead of time the S largest coefficients and were to build an approximation based on this, discarding all the coefficients after the S ones, and when they arrange in decreasing order of magnitude, I can give you this mean squared error. I cannot promise more, and nobody can. So now the question is it good enough? Like you put a person in an MR, and you say, this is my reconstruction error. Is this good enough? You're just saying, like, I go around London and I take pictures, and all my pictures are using, let's say, 10,000 bits, 10 kilobytes. For some images that might be good, for some others it might not be good. Other questions?
I'd like to ask about this. Is always like L1 is the same as L0 minimization? I mean, can L0 be always replaced by L1? Like in
No.
case of this dictionary, which consists of two alter bases, if we have certain requirements for L1, if we would need to use way more computational power, but use L0, can we get better results?
Yes, of course. And that's... So in general, you have the theory of underdetermined systems of equations, right? And then there's a theory that says that maybe there's one unique solution, right? So maybe, I don't know. There is right. What we're going to see that there is a theory of underdetermined. That's coming up in the lectures. But what I have is you give me y, you give me an A, right? Which is like this. And associated with A, I can compute a quantity, which I'm not going to tell you what it is now because we'll see it in tomorrow afternoon, I believe, which says that if this quantity is above a certain threshold, then all of a sudden I can have several sparse solutions to Ax equals B. Okay? So there's going to be an S bar such that if I could actually solve a combinatorial hard problem, I would, as long as the sparsity is below S bar, I am fine. But above S bar, we'll have that, there are actually several sparse vectors giving you the same data. Okay? So what we have is we have this picture of the world where there is an S bar here, and out beyond S bar, you're fundamentally ill-posed. We try to go around ill-posedness of underdetermined system by assuming sparsity, but this assumption will break down after S bar, because after S bar, you would say that here we have, for example, two solutions that are S bar plus one sparse that give you the same data. And which one would you pick? Here, there is a zone where if you could solve L0, you would be fine. But we don't know how to do it. Here, there is the L1 zone, where if the sparsity is below this, then L1 coincides with L0. Here, we don't know. Here, nothing works. And the gap is really, the gap of concern to us is really this. How big is this?
Any more questions? Well, if not, could I point out there's another talk at 4, which is Mike Davis. But could we thank Emmanuel once again?